Welcome back to Blocktical. So today we are going to see everything about the Ethereum. So from introduction to high level coding in the Ethereum, we are going to see everything right now. So first thing first, why we need Ethereum. So there are 3 points because of which we need Ethereum, right? We don't need different networks for different application or different purposes. Okay, so first thing is that now there is an inefficiency in mining, so to resolve that mining problem we need Ethereum. Then there is proof of work we are using in Bitcoin right now. In Ethereum also, Ethereum 1.0 we are using proof of work, but from Ethereum 2.0 we are going to use proof of stake, right? So for that we need Ethereum. Now, the initial idea of Ethereum was developed by Vitalik Buterin in 2013. A 19-year-old boy. Okay, what he did, he implemented the concept of smart contract. Okay, and again, the second point is 90% market covered by Ethereum, right now 90% of market is covered by Ethereum. So this is the basic of Ethereum, what Ethereum do. So the biggest question is, what is Ethereum? Okay, so Ethereum is a state transaction machine. And second point is, unlike Bitcoin, which follows UTXO model, right? Ethereum saves everything off chain. So whatever account you have on Ethereum, the things are getting saved off chain, right? Remember, currently Ethereum 1.0 is using proof of work, while in future Ethereum 2.0 is going to use proof of stake. This is a new consensus algorithm we are going to see in future. If someone is going to design the architecture overview of a web application which works on Ethereum network, now that particular application is designed in a 4-layer architecture. The first layer is application layer. The second layer is protocol layer. The third layer is network layer. The fourth layer is storage layer. So on application layer, okay, you are going to see smart contracts, or I would say decentralized applications. On protocol layer, you will see consensus algorithms, which is proof of stake or proof of work. On network layer, you will see a peer-to-peer network, and in storage layer, you will see label DB or rock DB. Okay, so this is the basic architectural design of a application in Web3 environment. Now the question is, what is Ether? So Ether is the currency or native cryptocurrency for Ethereum. So whenever someone do any transaction, they need to pay a fee in Ether. Remember, there are two things. One is reward and second one is transaction fee. These two are different things we are going to see later in time. So let's take a overview. So if someone helps you in accepting this particular transaction as a block, okay, now this person validates that, okay, this is a block. Now you have to pay reward to this person. Now this is a reward which you have to pay in Ether. Okay, now second thing is, when a functionality is getting executed on a smart contract, right, that execution will happen and cost you some gas. This gas can be your transaction fee. This is what is going to be paid in Ether. Now let's see difference between Ethereum and Bitcoin. In Ethereum, we have native currency as Ether. In Bitcoin, we have Bitcoin. Now second one is here we can store data. Here we can store transactions. Third point is here miner will get fee and reward. Here miner will get reward. There is a limit in Bitcoin of maximum Bitcoins, which is 21 million maximum Bitcoins. Whereas in Ethereum there is no limit, so Ether can be infinite. So where Ether can be infinite, we have to remember that within a month 18 million Ethers can be generated. So next point is gas. So gas is a unit to calculate the computational cycle. Now there is a gas price, which amount of gas per unit computational cycle. So when a computation cycle got complete, I have to pay one way or two way or three way. This is what gas price is. Okay, now gas price can be represented in G way, and G way is equals to 10 to the power 9 into way. So this is some pretty mathematics, okay, which you can do, you can learn. Basically in an Ether there are 10 to the power 18 way. So way is the lowest unit of transaction, or I would say Ether in the Ethereum network. So I mentioned that in a smart contract, when there is some functionality already written, to execute each line of code we have to pay gas fee in way. So let's consider there is a function for which I assign 25k way to complete the execution. Now there must be a case that in the middle our way got consumed till then, but our program is still left to be get executed. In that scenario we will say this is a scenario of out of gas. So in out of gas scenario, what will happen, that the transaction got terminated at this point, but the gas which is getting consumed will never return back to you. The gas price of Ethereum, or we can say the gas limit which you are fixing to execute, is very crucial point in Ethereum, right? It is because to complete that transaction, already executed operation deduct their fee from total transaction. Now comes Ethereum account. So an account in Ethereum are stored in global shared state in the form of key value pair. So remember, whenever you are storing an account on Ethereum, it will be in key value pair. So key always a 20-bit string, and your value will be anything. Now this 20-bit string will be a public key for user. What? Public key for user. Now if we say what the value will contain, so value has its own details. So let's try to define that. The value will contain a nonce. The value will contain a storage root. The value will contain a code hash, and the value will contain a balance. So every time when you put new transaction, okay, this value get increases. The storage root, or I can say the hash, is the Merkle tree root hash. So remember, there is a concept of Merkle tree and Merkle root. So this root is going to be stored here. Now the code hash is the hash of the code of a smart contract. Okay, so only in the contract account this value get saved. Now in the balance will be saved in ether for an account. This nonce will provide the number of transactions sent from that particular account. Okay, so let's take a key. This particular A has some key. It spent 5 transactions, so the value of nonce will be 5. Next time if he do some transaction or she do some transaction, the value will increase to 6. Next time that value will increase to 7. So this way the nonce value will increase. So remember, in Ethereum there are two types of account. One is EOA and second one is CA. EOA stands for externally owned account and CA stands for contract account. Externally owned account are controlled by private key, and these account doesn't have any code hash in their value. Okay, remember, these account doesn't have any code hash. These account will have the hash of the code, because these account will save the code base of smart contract. Remember, in this EOA, the code hash field will contain the hash of empty string. An externally owned account may be owned by a person or an organization and connected to blockchain to an external agent. So remember, I mentioned you that externally owned account can call externally owned account, and on the other hand externally owned account can call contract account, and this contract account can call another contract account. So this is what we call transaction value, or we will call value transaction. This transaction we called as message transaction or message call transaction. This transaction we will call as message. So remember, we have three kind of things: value transaction, second one is message call transaction, and third one is message. Okay, so this will happen when an externally owned account call the externally owned account. This will happen when externally owned account will call the contract account. This will happen when contract account will call the contract account. Let's talk about the anatomy of a transaction in Ethereum. So first thing which it contains will be nonce. Then the gas limit. So how many gas are only allowed to do the transaction. Then gas price. This will tell the gas price, okay, per unit price of gas. To whom you have to send the data, the value of transaction you are going to send. Then there are three flags V, R and S. These are the three flags. Then there is one for data storage and one for INID. So these three flags used to generate the signature that identifies the sender of the transaction. Okay, so together these three will make sure that who send the transaction. Now this init will contain a code fragment that is used to initialize the new contract account. So this data will store the value of this. So when an externally owned account call that contract account, it will store the transaction message call. Then externally owned to externally owned, it will call the value transaction. Previously we saw the anatomy of a transaction. Now let's see the block anatomy. So block will contain first block header, second the set of transaction included in the block. So it will contain transaction 1, transaction 2, transaction 3, all the set of transaction which is getting included in this block, and the third one set of the other block header from the current block Omer. It will contain the header of Omer block. So Omer, there is a concept of Omer blocks or uncle blocks. So it will contain the header of this Omer and uncle blocks. Okay, so these are the anatomy of a block in Ethereum. So let's take block header and try to discuss it more. Block header in Ethereum will contain parent hash, then it will contain nonce, then it will contain difficulty level, then it will contain mix hash, then it will contain timestamp, and this timestamp along with timestamp it will contain gas price, gas limit used to mint that particular block. Okay, then uh, it will store the state root, then it will store the transaction pool, or I would say transaction root, then it will store the receipt root. So these are the three important roots which it will store. We will going to discuss more in detail later in time. So first point is the state root. State root will store the Merkle root of the current state. So the current state which this particular Ethereum network has. So the state root will store the root of that particular current state. Okay. Then comes to the transaction root. So whatever transaction this particular block contains, so it can arrange in T1 T2 format, and whatever root get calculated at the point of this particular Merkle tree of transactions, it will store the transaction root for that. Then the receipt receipt root will contain the Merkle root for all the receipts for all the transaction in the block. So transaction 1 will contain a receipt, transaction 2 will contain a receipt. The same format for all the receipt, it will generate a Merkle root, and that Merkle root can be stored in the receipt root. So remember, a receipt is issued by the network system whenever a transaction is committed. So state of the blockchain network equals to all the three roots, which is state root, transaction root, and receipt root. So these are the part of a blockchain header. Okay. Now network state in Ethereum is captured every time a block is created, and since the block creation rate in Ethereum is about 15 seconds, we can say capturing the time of network state is about 15 seconds. Now block body contains all the transaction including in the block. Maximum of you heard about Etherscan. So let's discuss what is Etherscan. It is a blockchain explorer. So here you can see all the data which is there on the blockchain network. Remember, whenever you are going to do a transaction, there is a minimum gas fee which you have to pay, which is 21,000 gas. Now gas used for a pure ether transaction is 21,000. There is a very important topic which we call as Byzantine journal problem. So this is a concept where we have four journal: journal 1, journal 2, journal 3, and journal 4, and these four journal want to capture this fault, and these four journal are in the same team. Now remember, out of these four journal, this journal 3 is corrupted whenever the time of attack was there. So let's say the four journal decided, okay, they are going to attack sharp 9 a.m. to the fort to capture that particular fort. So at sharp night 9 a.m. journal 2 initiated the transaction, and they want to, okay, attack. Now at the same time, journal 1 received the attack signal, so he received it and he flooded it to its nearby link journals. Okay. Now at the same time, journal 3 decided, okay, I am the corrupted one, so I don't have to attack. So he decided, don't attack, and he flooded that don't attack. Now see the journal 4 who got one attack and one don't attack scenario. He is not able to decide what to do right now. So there is a problem right here. So this problem we are going to call as Byzantine journal problem. So this is a problem you can learn in game theory. So let's take f is the number of nodes which are corrupted in a network, okay, or we can say falsy nodes. Then total number of nodes in a system can be defined in a proper system which is working actually can be defined as 3f plus 1. So this is how we can say this is a working network. Okay, so remember this. These 2 points are important. So remember, we are just now resolve the one journal problem where one journal is corrupted. Now in the same case where we have 4 journal, if 2 journals are corrupted, that problem is still not resolved. Now what is the ways in which we can resolve that issue? So first one is slashing, second one is encryption. Okay, now using these two techniques along with some other techniques, we can ask each journal to put something on stake. Okay, if they put something on stake, then if we found the network found them guilty or corrupted, then that stake will captured from them and they will lose that particular stake. Okay, so they have something to lose, so they don't want to be falsy in that case. So this is how we can resolve the issue, but proper formulation of that cannot be derived yet. Now there are different consensus algorithms, which is proof of work, second one is proof of stake, third one is dedicated proof of stake, then fourth one is proof of authority, which testnet will use like Robston and Rinkeby. Then proof practical Byzantine false tolerance is there. Then FBFT is there, which is 70% theoretical, but there is a network which we call as Stellar. This network is using this FBFT. So what is proof of work? So here a task is given to you where you have to resolve this task, and to resolve this task you have to do a computational heavy work, and that's why we are calling it as proof of work. Ethereum 1.0 uses proof of work but little bit modified. So he captured some of the things, like there is an algorithm which is known as Dagger Hashimoto algorithm, and along with that he uses data structure as DAG. So he combined this and created their own proof of work algorithm which we call as Ethash. So we are going to see this in detail. There is a concept of forking, type of forking, intentional forking or unintentional forking. Now whenever something in a chain, whenever a fork happens, right? So suppose here a fork happened. Now the chain is distributed into two. Now there is a two chain links. So at a particular time, after a particular time, we are going to select the longest chain and we are going to prioritize that. So it will create a new chain and it will reject these blocks which is getting mined. So these blocks get rejected and these blocks get accepted. So this is we call as longest chain rule. At any given point, the time node should follow the longest chain available to them. Now I mentioned you uncle and omer blocks. Now here if we talk about this particular block, so for this block this is uncle block or omer block. Okay, because at the same time they provided the solution. So suppose there is a proof of work task given to you. Okay, this is the task. Now two blocks reported the same task at the same time. So block 1 and block 7 reported the same task at the same time, but anyhow the blockchain network supports block 1. Okay, now it is not a good way to reject block 7 because he also did the same work with the same pace, right? So this block is getting saved as a uncle block or omer block, and this block is also get rewarded. So remember, this is the first time in Ethereum where we are going to reward the uncle blocks also. So logs and receipts. So remember, whenever is smart contract we are going to define events also. Sometimes we need events to listen to them, and these events will log the data. Okay, these log will contain logger account address. So first one is logger account address, second one is series of topic represented various events. So it will contain events or series of events. Okay, and it will contain the data associated with that event. Okay, so these are the three things which it holds. Now talk about the receipt for each transaction in Ethereum, right? Remember, we are going to create a receipt hash. So for each transaction we are going to receive a receipt from every peer. So this receipt will contain the block number, block hash, transaction hash, then gas used for that particular transaction, then commutative guess of the current block, and lock created using the particular transaction while executing it. So these are the all things this particular receipt will hold. Okay, these 6 things majorly. So whenever a transaction happen in Ethereum, there are some checks which will happen. So first one is formatting, second one is signed, that particular transaction is signed or not. Third one is nonce is there or not in that particular transaction, which is proper nonce or not. And fourth one is gas limit, which is greater than the 21k gas. And fifth one is balance is upfront or not. Okay, so these all are going to be checked. So how the gas fees is calculated? Remember, there is a formula that 21k is already used and 4x is getting used for every 0 byte which is there, and we have to add 68 for non-zero byte. Okay, so this is the basic formula to calculate the gas fees in Ethereum. Now when we do the process, right, so while doing the process, the deduction of gas fees or the upfront will happen on the first, then it will increase the nonce. Okay, and it will do the operation, whatever the operation is. Okay, now finally it will update the account state or the state. Now the next point is altcoin and token. So altcoin is nothing but the base coin for any network. So in Ethereum case it is Ether, whereas the token is something standard which we define. So a token may be a fungible token or a non-fungible token or something else which is defined based on the standards. So for fungible token we have a standard called EIP20, and for non-fungible token we have EIP 721. EIP stands for Ethereum Improvement Proposal, and the 20 will define the standard number which we have. Now these fungible and non-fungible are different topics right now, but we are going to see later in time. Now to understand the token can be bought by using Ether. So you can buy any fungible or non-fungible token by paying using Ether, or someone will just give you that particular token in reward. Okay, so remember, these are the differences, these are the major difference between altcoin and token. Now there are some challenges which Ethereum will have. So the very first challenge which Ethereum faces, throughput. The speed of network will support 2k transactions per second. Okay, but whereas in Visa, so if you heard about Visa, that transaction is getting supported 21k transactions per second. So still we have to move from 2k to 21k, right? Then the second one is cost. So Ether, whenever you do a transaction on Ethereum, it is very expensive, so we have to limit that out. Then third one is decentralization. So proof of work, definitely mining process. Okay, so suppose there are some 5 mining pools right there on the network which hold the 61% of the complete mining authority. So whenever a 51% attack need to be done, so only these 5 major pools will come together and do that particular attack on the network, right? So this is the issue of decentralization in Ethereum. Now the fourth one is size. So we have to increase the size of blocks so that we can hold the maximum transaction in a single block, because if you see, the rate of increasing is very exponential. So when in the initial days the people are only doing the limited number of transactions, but these number of transactions are growing bigger and bigger exponentially. So somehow we have to adjust that out, right? So whenever you talk about the Ethereum, we have a user interface which we called as DApp, decentralized applications. So these are not that much user friendly, right? So we have to make them user friendly. Ethereum is not quantum resistant. So this is a big word, quantum resistant. Just comment down if you want. I will make a new video in this particular topic. Now the most recent challenge which is getting added to this particular Ethereum network is the rising of emerging competitors. There are different consensus algorithm called proof of stake, neo, or something else, right? So there are competitions which is available there, which is using some different consensus algorithm to support the consensus mechanism, supporting more than 21k transaction at once in one second. So I talk about the challenges which Ethereum network is facing. Let's talk about the solution. So first thing is we have to change the consensus algorithm. Okay. So because when we change the consensus algorithm, maybe we are going to support more transaction at once. So right now Ethereum 1.0 is using Ethash, which is a proof of work based consensus mechanism. Now they are shifting to Ethereum 2.0, which will use a proof of stake as their major consensus mechanism, right? Then second one is increasing the throughput. So you can increase the block size, or something other way you have to increase the throughput also, because to increase this throughput you can also save data in off chaining. So there is a scenario where you can save all the data in off chain and then the root of that particular data on the on chain. So there are different concepts which you can play around. So to increase the throughput of Bitcoin, right? Remember Bitcoin. So to increase the throughput of Bitcoin, there is a network called Lightning Network, which introduced the concept of storing off-chain data and then putting hash of it on the blockchain network of it, Bitcoin, right? So that is how we can increase the throughput of a network, right? Now the third one is sharding, which is a practice of horizontally partitioning the blockchain network as we do in the NoSQL databases. Next concept is Merkle Patricia tree. Now this we call as MPT. So first thing here which come is radix tree. So remember from data structures or algorithms you heard about radix tree. So let's there are four words. First one is argon, second one is Armenia, third one is astro, and fourth one is asterisk. So all the four words are started with A. Now two words contain R and two words contain S. So I divided that into two child nodes, R and S. Now with R we have GON in one, and in second we have mania. With S we have TRO. Okay, so we can also divide this, we can also write this T here as T, then we can say RO in one place and IC in another place. So if I want to go to read maniac, so how can I use AR and then maniac? So this is how I can save it. So this is a way where we can store the data, right? So the modified Merkle Patricia tire uses key value pair to store the value of the tree. The key is a pointer to the state of the Ethereum, and the value is the actual state of the Ethereum network. In the Bitcoin Merkle tree, you can only verify whether a particular transaction has been tampered or not, but by checking its hash value, right? But in Ethereum, you can use the Merkle Patricia tree to verify and check what exactly is tampered with. So later in time, if I want to save this particular thing in Ethereum, right? If I want to tamper this asterisk to STK, okay, so this is getting highlighted that okay, A is correct, ST is correct, okay, this is the only node which is getting tampered. So we can find out the particular node. In Bitcoin, only the details that okay, this is tampered or not, that is getting resolved. But here you can also identify what is getting tampered, what particular value is getting tampered. So remember, in Ethereum we are going to use MPT. As you know, Ethereum is a state machine which you learn in automata, or we can say theory of computation, where Bitcoin is transaction based blockchain, where Ethereum is a state machine, right? Bitcoin uses Merkle tree or Merkle hash, whereas Ethereum uses MPT. Let's talk about different type of consensus algorithm. First one is proof of stake, where we have validators. Okay, so to become a validator, you have to qualify eligibility, the eligibility that you have to stake 32 ether at once in taking part of a particular transaction support. Now there are only limited number of transactions which can support this, and those are the validators which can validate the particular process is correct or not. Now second one is how to increase the throughput. You can use the sharding, or I can say slot, okay, which we use in NoSQL databases. Third one is it is energy efficient, okay. Now fourth one is it uses dynamic reward based on stake. So whatever stake you put, minimum is 32 ether. Based on that, you get rewarded. Now second one is delegated proof of stake, where a bid will happen, okay, you will vote and you will get reward. So the higher your stake is, higher your voting power will be. Higher your stake is and higher your voting power. So this is how the delegated proof of stake will work. Then comes proof of authority. Proof of authority, your identity is on stake, okay. So basically if you do wrong, you will remove from that particular authority. So commit block done by or through the set of authority nodes in a particular network. Then comes the PBFT, practical Byzantine false tolerance, which contains three stages. So there are three stages. One is pre-commit, second one is prepare, and third one is commit. This is a two-step process where leader tells everyone to commit, okay. Now every node prepare and broadcast the block on the particular network. So this is a leader pair which tells everyone to commit. Now everyone in the network will broadcast to each other what is going on in the network, okay, whatever the transaction is. Now leader plus other nodes reaches quorum, then commit the block. This PBFT is getting used by Facebook in its network called Libra. Its cryptocurrency is Dime. So remember, the algorithm which they call is as Libra BFT, or which is derived from PBFT plus hot stuff. So these two algorithms get combined to create the Libra BFT. Now Ethash. So remember, Ethereum implemented this. Ethereum 1.0 implemented Ethash. So this particular algorithm is based on proof of work, which is using Dagger's Hashimoto algorithm, which contains DAG, directed acyclic graph. Remember that proof of work is work incentive, that you have to consume many resources over here, but in Ethash you have to consume resources as well as you have to do some input output operations. So this is input output intensive along with proof of work. So we are going to learn two separate algorithms differently, and then we will try to combine them together. First one is Dagger algo. This algorithm uses directed acyclic graph. This is a huge dataset used to store a lot of data in the most optimized way. This is input output operation like shifting, moduling. Hashing is still in use, which means mining was still an issue. In this case, we are going to use hashing also. Now if we are using hashing, then again the problem is mining, okay. We are used to do mining for that. Now second one is Hashimoto algo. So Hashimoto is nothing but hash plus shift plus modulus process. Last process equals to XOR, okay. So whatever the process you are doing, in the last you have to do an XOR of the transaction. So this particular algorithm is memory hardened because block number is getting calculated at every step, or I can say at every single iteration. So number of transaction, if I say 64, then the number of times it will calculate the block number is 64 times. Next topic is smart contract development on Ethereum. So here we have to introduce you to the DApps. So there are multiple layers in an application. and an application can be divided into 4 major layers, which I already mentioned previously. So first one is front end, then back end, then communication, then database. So these are the 4 layers which we can define a particular network in. Now, to make application decentralized, either you make any one of the layer decentralized or whole all layers as decentralized. So Ethereum decentralize the backend layer. Remember, Ethereum decentralize the backend layer or the logic layer. I can say this is the logic layer also. It does so by mean of smart contracts. So here we have smart contracts in running. So because of these smart contracts, we can make this particular layer decentralized. Let's talk about DApp architecture. So here we are having a user interface. So we will call it as UI. Now this user interface will use Web3 library, or we can say Web3.js library if we talk about JavaScript. Then this Web3 will interact with the smart contract. Okay, and this is a peer. This whole process is done in peer 1. Now this peer smart contract will help, or this peer is getting connected to another peer. This is getting connected to another peer. This is getting connected to another peer, and so on. So later in time, if you see, these peers are communicating. So this smart contracts. So if you see, this smart contract can inherit different smart contracts that derived from different peers, or I can say deployed by different peers on the network, right? So we can say that decentralized applications are always distributed in nature because everything is distributed over here. Now let's talk about smart contracts. So first one is these are computer program. Second one is these are deterministic, like if you put some input, they will change the state, or they have to move from one state to another state, or will remain on the same state. So these are deterministic, like you will get a state. It is not like like you will not get any ambiguity in defining where it need to go. Now third one is these are immutable but deletable. These smart contracts are immutable, but it can be deletable. So if you deploy a particular smart contract on a particular address, so suppose this is the address of a particular smart contract, and your smart contract is written over here. So you can erase this particular code which is written over here, but you cannot immutable. You cannot change this particular code. Now fourth one is limited execution context. So you have only 4 contexts to execute this, which we are going to discuss later in time. So limited execution context. Then fifth one is language. So we have different languages right now. So mostly we use Solidity in Ethereum to deploy the smart contract or to write the smart contracts. Then sixth one is contract creation transaction. So this will happen when you deploy a particular network, or you do a transaction to a 000 kind of address. So when you hit this particular address in the to field of a transaction detail, then it will remember that okay, this is a contract based transaction, and it will create a contract address for that. Seventh one is delete, but contract account will not be deletable. So the 7th point is that you can delete this particular contract, but the account at which particular contract is hosted, that cannot be deleted. Next point is EVM. So EVM stands for Ethereum Virtual Machine. Is a runtime environment on which smart contracts are executed. So if you write a smart contract, you have to deploy it on EVM. So that when you deploy it on EVM, that functionality will work, and network can handle that functionality. The smart contract code need to be compiled to the EVM bytecode. So this particular EVM will support the bytecode. Okay. So first, in whatever language you are writing the smart contract, you have to compile it. So for Sol, or I can say Solidity, we have Sol-C as a compiler, in which we are going to compile it, and we are going to convert it to the bytecode. Then we have to feed this bytecode to EVM, and then this EVM will execute that functionality. Now EVM installed on every node or client in blockchain network. So if I have a blockchain network, okay, so at every node in this particular network, this particular EVM is deployed. Remember, no peer can have the access to EVM code. Okay, they cannot see the programs of EVM. This is called as sandbox. This is called as sandbox. The second concept is isolated. So whatever happening on one peer cannot be visible to the another peer. Remember, I talked about EIP 20 or EIP 721 and told that EIP stand for Ethereum Improvement Proposal. So to update the EVM, okay, we have to provide the EIPs, and whenever we talk about the EVM code or the standard code, we have to define it as a proposal, and when all the community or the majority of the community accepted that proposal, then we have to make it as permanent in the community. So currently the version which we are using for EVM is St. Petersburg. Okay, remember this. St. Petersburg is the version which we are using currently as a EVM. Now there are three locations to store data on EVM. So whenever we talk about EVM, then there are three storage for the data. So first one is we can store it in storage, then in memory, and then in stack. So storage is persistent, it's kind of a permanent storage. Memory is volatile. This, whenever we come out of that particular functionality, this memory data will get erased. And stack is size maximum. Now the maximum size of this stack is 1024 byte into 256 byte. So this is the maximum. So this is 1K and this is 256 byte. So EIP is kind of a new feature to do the bug fixes or to add the new features. We have to propose the EIP to Ethereum development community. If accepted, they can include the particular changes in the next version.